A star has the weight of a universe pressing inward. A fusion reactor has steel, magnets, mathematics, and almost no room for error. Inside its chamber, hydrogen must become hotter than the sun's core, remain suspended without touching the walls, breed its own rare fuel, and release enough energy to power not only the grid, but the machine itself. Fusion is not impossible. In many ways, it already works. The mystery is why making it useful remains so extraordinarily difficult. Thank you for spending part of your day or night here. Please leave a comment with the time you're watching and the place you're listening from. It is always fascinating to see how far these quiet science journeys travel. A like helps this documentary reach more curious minds. Subscribing keeps future explorations close, and sharing it may bring someone else into the same calm orbit of discovery. Now, let the magnets rise, the plasma glow, and the deeper story of fusion begin. Fusion has spent much of the modern age standing just beyond reach, close enough to inspire confidence and distant enough to invite doubt. Its promise is easy to understand. The same basic process that powers the sun appears to offer an energy source with immense fuel reserves, no carbon released during operation, and far less long-lived radioactive waste than conventional nuclear fission. In its most hopeful form, fusion suggests power plants that run on forms of hydrogen drawn from water and on tritium bred from lithium, producing heat without burning coal, oil, or gas. Such machines could support electrical grids, heavy industry, desalination, synthetic fuels, and other systems whose limits are often set by the price and availability of energy. Yet the distance between that promise and a working commercial reactor remains wide. Fusion is not difficult because the principle is mysterious. It is difficult because every part of the principle must be made to happen at once, under extreme conditions, inside a machine that must survive, repeat the process, and eventually sell electricity at a competitive price. The history of fusion research therefore carries a peculiar tension. Progress is real, sometimes dramatic, but each achievement reveals another layer of engineering that had been hidden behind the previous goal. The earliest challenge is simply to make atomic nuclei join. The nuclei of light elements carry positive electric charge, and positive charges repel one another. At ordinary temperatures, hydrogen nuclei approach, feel that repulsion, and turn away long before the short-range strong nuclear force can bind them together. A fusion reactor must give the nuclei enough energy to cross that barrier. The usual method is heat. When a gas is heated to extraordinary temperatures, electrons separate from atomic nuclei and the material becomes plasma, a restless mixture of charged particles. At temperatures reaching well beyond those inside the center of the sun, some nuclei move fast enough to collide with sufficient energy for fusion to occur. This part has been achieved many times. Fusion reactions are created in laboratories, in magnetic confinement devices, in laser-driven experiments, and in other machines designed to compress or heat fuel. The central scientific fact is no longer in doubt. Fusion can be produced on Earth. The deeper problem is making it produce more useful energy than the entire system consumes, and then making it do so reliably for years. A single fusion event releases a tiny packet of energy. A power plant needs an astronomical number of such events every second. The plasma must therefore remain hot, dense, and confined long enough for reactions to become common rather than rare. These three requirements form a narrow path. If the plasma is hot but too thin, nuclei seldom meet. If it is dense but escapes quickly, its energy vanishes into the walls. If it is confined but cools too rapidly, the reaction rate collapses. Each improvement in one area can make another area harder. Stronger heating can drive more violent turbulence. Higher density can make the plasma harder to control. Longer confinement can expose materials to greater heat and radiation. Fusion research becomes a long effort to balance conditions that naturally resist balance. The Sun solves this problem through scale and gravity. Its enormous mass compresses hydrogen at its core, while its vast volume provides an almost unimaginable number of particles. Even a reaction with a very low probability becomes significant when so much fuel is present for so long. A reactor on Earth has no such gravitational prison. It must create a small artificial environment in which particles behave as though they are deep inside a star, then prevent that artificial star from touching the machine that contains it. No solid wall can hold plasma at fusion temperature. Any direct contact cools the plasma and damages the surface. Magnetic confinement devices therefore use fields to guide charged particles away from the walls. The leading approach, the tokamak, shapes the plasma into a ring and surrounds it with powerful magnets. Another approach, the stellarator, twists the magnetic geometry into a more complex form intended to provide steady confinement. Both designs rely on the fact that charged particles spiral around magnetic field lines, yet a plasma is not a quiet substance. It carries currents, forms waves, develops instabilities, and generates turbulence. Small disturbances can grow. Energy leaks outward. In severe cases, the plasma can abruptly lose confinement, ending the reaction and placing sudden stress on the machine. The challenge is not merely building a magnetic bottle. It is keeping the bottle stable while the contents constantly push, twist, and rearrange the field. This is one reason fusion often seems to retreat as researchers approach it. A device may reach a record temperature, but only for a short pulse. Another may confine plasma for longer, but at lower performance. A third may produce a burst of fusion energy, while the surrounding facility still consumes far more electricity than the fuel releases. Each result matters, but no single result equals a power plant. Public discussion often compresses these distinctions into one phrase: net energy. Though that phrase can refer to several different boundaries. One experiment may compare fusion energy with the energy delivered directly to the fuel. Another may compare fusion energy with the power used by heating systems. A commercial station must meet a much stricter test. It must cover the energy consumed by magnets, pumps, cryogenic equipment, fuel processing, cooling systems, and all the other machinery required to keep the reactor operating. It must then convert the remaining energy into electricity, send that electricity to the grid, and do so often enough to pay for construction, maintenance, and eventual replacement of damaged components. A scientific gain is therefore not the same as an engineering gain, and an engineering gain is not the same as an economic gain. The dream becomes more demanding at each step. Fuel adds another layer of difficulty. The reaction most often chosen for near-term reactors combines deuterium and tritium, two heavy forms of hydrogen. This pairing is favoured because it fuses more readily than many alternatives at achievable plasma temperatures. Deuterium is abundant in water, but tritium is rare, radioactive, and difficult to store. A future reactor cannot depend on a large natural supply because no such supply exists. It must produce tritium inside the plant by using neutrons from fusion reactions to interact with lithium in a surrounding blanket. This means that a reactor must not only burn fuel, it must manufacture part of its next supply while operating. The breeding system must recover enough tritium to replace what is consumed, compensate for losses, and provide reserves for processing and startup. At the same time, the blanket must absorb neutron energy, carry heat away, shield magnets, and survive intense radiation. A component that appears secondary in a simple diagram becomes central to the entire machine. The neutrons themselves create another contradiction. Magnetic fields can confine charged particles, but neutrons have no electric charge, so they fly straight out of the plasma. This is useful because they carry most of the reaction energy into the blanket, where it can become heat. It is also destructive because those fast neutrons strike atoms in solid materials, displace them from their positions, and gradually change the structure of the metal. Over time, materials can swell, become brittle, lose strength, and turn radioactive through activation. The inner wall of a reactor must withstand heat loads, particle impacts, and neutron damage while remaining compatible with a vacuum and a delicate plasma. Even if the plasma performs perfectly, the machine around it ages under conditions that no conventional power station experiences. Replacement is not simple. Components near the chamber may be too radioactive for direct human access, so maintenance must be done remotely. Every repair affects operating time, and every period of inactivity affects cost. Fusion's difficulty therefore lies in accumulation. None of its individual problems is necessarily impossible. Magnets can become stronger, plasma control can improve, materials can be tested and replaced, tritium can, in principle, be bred from lithium, heat can be converted into electricity. But a power plant succeeds only when all these systems work together, continuously, inside one design. The machine must be a physics experiment. A fuel factory, a high-temperature furnace, a radiation shield, a remote maintenance facility, and an economical generator at the same time. The promise has not vanished. It becomes more precise. Each decade replaces vague optimism with a clearer map of the obstacles. That map is daunting, yet it is also evidence of progress. Fusion remains difficult not because science has failed to understand what must happen, but because nature demands that many extreme conditions be satisfied without interruption. The dream still recedes, though it no longer recedes into mystery. It recedes into engineering, materials, fuel cycles, reliability, and cost, where the remaining distance can be measured even when it cannot yet be crossed. At the heart of fusion lies a struggle between two forces that act on very different scales. One is familiar across ordinary matter, the electromagnetic force, which causes like charges to repel. The other is the strong nuclear force, which binds protons and neutrons together inside atomic nuclei. The electromagnetic force reaches across comparatively long distances, while the strong force acts only when particles come extremely close. This creates the central difficulty. Two hydrogen nuclei may be moving toward one another, but each carries a positive electric charge. Long before they approach closely enough for the strong force to bind them, their electric fields push them apart. The barrier is not a solid wall, yet it behaves like one. It is often called the Coulomb barrier, after the law that describes the force between electric charges. Overcoming it requires energy, and in a fusion reactor that energy is supplied mainly through heat. Heat in this setting is not warmth in the ordinary sense. It is the motion of particles. A hotter plasma contains nuclei moving at greater speeds, with a wider spread of energies. Most collisions still end in deflection. A few nuclei approach nearly head-on, carrying enough kinetic energy to come far closer than the average particle. The goal is not to make every collision produce fusion. The goal is to create conditions in which enough rare collisions succeed that the released energy can support the plasma and ultimately power the machine. This is why fusion is a statistical process. The reactor does not select individual nuclei and push them together. It creates a vast population of particles and depends on probability. Temperature changes that probability by reshaping the distribution of particle speeds. Even in a plasma with a defined average temperature, particles do not all move at the same rate. Some are slower, some are faster, and a small fraction form a high-energy tail. Those unusually energetic nuclei are especially important because they have a better chance of approaching through the electromagnetic repulsion. Fusion begins in that tail before the average particle has enough energy to cross the barrier in a purely classical way. Yet classical motion is only part of the story. Quantum mechanics allows a particle to appear on the other side of a barrier that it could not normally climb over. This effect is called quantum tunneling. The nucleus does not travel through a hidden tunnel in space. Instead, its quantum state has a small probability of extending beyond the region forbidden by classical physics. When two nuclei come close enough, tunneling gives them a chance to reach the range where the strong nuclear force can take control. Without this effect, many fusion reactions would require even more extreme temperatures than stars or reactors can provide. Tunneling makes fusion possible, but it does not make it common. The probability remains tiny unless the nuclei approach very closely, and that still requires substantial energy. The fusion rate therefore depends on a narrow overlap between two probabilities. High-energy collisions become less common as particle energy rises, while tunneling becomes more likely at higher energy. The collisions that contribute most strongly sit in a band where these two trends meet. In stellar physics, this region is often described as the gamma window. It is not a physical opening but a range of energies where particles are both common enough and energetic enough to fuse at a meaningful rate. In a reactor, heating the plasma shifts more particles into this useful range. The choice of fuel also changes the shape of the problem. Different nuclei carry different charges and have different internal structures, so they do not face identical barriers or react with equal probability. Reactions involving heavier nuclei generally confront stronger electrical repulsion because the total positive charge is greater. This is one reason hydrogen isotopes are favoured. Their nuclei each contain a single proton, giving them the smallest possible positive charge for an atomic nucleus. Even then, ordinary hydrogen is a poor practical fuel for terrestrial reactors. The chain of reactions that powers the Sun begins with proton-proton fusion. But the first step is extraordinarily slow. It depends on the weak nuclear interaction, which must transform one proton into a neutron during the process. The slowness is beneficial for a star because it allows the Sun to shine steadily for billions of years. It is useless for a compact power plant, where energy must be released at an immense rate inside a limited volume. Terrestrial fusion research therefore turns to isotopes that react more readily. Deuterium contains one proton and one neutron. Tritium contains one proton and two neutrons. Their electric charges are still only +1, so the electromagnetic barrier does not increase. But their nuclear structure makes the deuterium-tritium reaction far more probable than proton-proton fusion at achievable temperatures. When deuterium and tritium fuse, they form a helium nucleus and release a fast neutron. The reaction gives back much more energy than the colliding nuclei carry into it, because the products have slightly less mass than the original fuel. The missing mass appears as energy according to the relationship between mass and energy. This gain is the reason fusion can become a power source at all. Yet the gain from each successful event does not erase the cost of creating the conditions that make those events frequent. A reactor must heat a large amount of plasma, confine it, and compensate for every path by which energy escapes. As temperature rises, radiation losses can increase. Electrons emit energy when they are accelerated by electric fields near ions, producing Bremsstrahlung or breaking radiation. Impurities from the reactor walls can make this worse because nuclei with larger electric charge cause stronger radiation losses. A tiny amount of unwanted material can therefore cool the plasma disproportionately. This is another consequence of the same electromagnetic force that creates the Coulomb barrier. It resists the initial fusion collision, and it also provides routes for energy to leak away through radiation. The plasma must remain hot enough that fusion heating exceeds these losses, but raising temperature is not an unlimited solution. Magnets, heating systems, and plasma-facing materials all operate under practical limits. Higher temperature may improve the reaction rate, yet it can also intensify turbulence, increase wall loads, and demand more external power. Fusion engineering is forced to search for an optimum rather than simply pursuing the hottest plasma possible. The idea of ignition emerges from this balance. A plasma reaches ignition when the energy deposited by fusion products is sufficient to maintain the necessary temperature without continuous external heating. In deuterium-tritium fusion, the charged helium nucleus remains trapped by magnetic fields and transfers much of its energy to the plasma. The neutron escapes the magnetic confinement and carries most of the reaction energy outward. The helium particle can therefore help keep the fuel hot, creating a form of self-heating. But ignition requires the rate of successful fusion events to become high enough before conduction, radiation, turbulence, and escaping particles remove the energy. The barrier between nuclei is thus connected to every larger challenge in the reactor. Because fusion probability is low, the plasma must be hot, because it must be hot. It cannot touch ordinary walls, because it cannot touch walls. It must be confined by complex magnetic fields, or compressed for extremely brief periods. Because confinement is imperfect, energy leaks out. Because energy leaks out, the reaction rate must rise further. Each requirement grows from the first act of resistance between two positive charges. Even the word collision can be misleading. Nuclei in a plasma do not behave like hard spheres. Their paths bend gradually as electric fields act across distance. A close approach is a carefully shaped encounter governed by speed, angle, charge, quantum probability, and the internal energy levels of the nuclei. Many particles pass one another without reacting. Some scatter and transfer energy. A very small fraction enter the right conditions for fusion. Reactor design works by multiplying these rare chances across an enormous number of particles. The plasma may contain countless nuclei, yet only a tiny proportion fuse during any instant. A useful machine depends on maintaining the population long enough, dense enough, and energetic enough that this tiny fraction still produces a large flow of power. This is the first reason fusion remains so difficult. Nature does not forbid the reaction, but it protects the nucleus behind a barrier that is easy for a star to challenge and hard for a machine to sustain. The strong force waits at a distance smaller than an atom by many orders of magnitude. While electromagnetic repulsion dominates almost the entire approach, heat brings nuclei closer. Quantum tunneling offers a narrow chance, and favourable fuels improve the odds. But none removes the underlying resistance. Every fusion device is built around this small and stubborn gap. The final distance between two nuclei that would release energy if only they could come close enough. Once fusion fuel is heated beyond the point where atoms can remain whole, matter enters a state that is neither ordinary gas nor liquid nor solid. Electrons separate from their nuclei, leaving positively charged ions and a sea of free electrons. This state is plasma, the working substance of most fusion reactors. Plasma is common across the universe. Stars, nebulae, solar winds, and lightning all contain it. On Earth, however, stable plasma at fusion temperature is profoundly unnatural. Every surrounding surface is cold by comparison, and offers a path for energy to escape. A reactor must create matter hotter than the centre of the sun while preventing it from touching anything solid. No conventional container can survive direct contact with fusion plasma. The machine must hold the fuel without holding it in the ordinary mechanical sense. Magnetic fields provide the closest solution because charged particles respond to them. An ion moving through a magnetic field does not continue in a straight line. The field bends its path into a spiral around an invisible line of force. Electrons do the same, though their smaller mass gives them tighter motion. By arranging magnetic field lines into a closed shape, engineers can guide the plasma away from the walls and encourage particles to circle through the chamber again and again. The field acts as a container made not of matter but of geometry. It is not perfect. Particles still drift, collide, scatter, and escape. Yet if the magnetic structure is strong and carefully shaped, it can slow those losses enough for fusion conditions to develop. The torus, a shape like a hollow ring, became central to magnetic confinement because it allows field lines to close on themselves. A straight magnetic tube would leak particles from its open ends. Bending the tube into a ring removes those ends, but it creates another problem. The magnetic field becomes stronger on the inner side and weaker on the outer side. Charged particles respond to this unevenness by drifting across the field, gradually separating according to charge and destabilizing the plasma. The solution is to twist the field so particles spend time on both sides of the torus and their drifts partly cancel, in a tokamak. This twist comes from combining fields generated by external coils with a powerful electrical current driven through the plasma. The current turns the plasma into part of the magnetic system. This can provide strong confinement, but it also makes the plasma vulnerable to disturbances in that current. In a stellarator, the twisting is produced mainly by complex external magnets. The coils curve around the chamber in elaborate forms, creating a three-dimensional field without relying on a large plasma current in the same way. This can support steady operation, but the geometry is much harder to design and manufacture. In both machines, the aim is to create magnetic surfaces nested inside one another, with the hottest plasma near the center and cooler plasma toward the edge. The center must remain isolated from the material chamber. Even a small increase in transport from the core to the edge can drain energy faster than fusion returns it. The word confinement suggests stillness, but the plasma is never still. Particles race in spirals, bounce between regions of stronger magnetic field, drift across curved geometry, collide, and respond collectively to electric and magnetic forces. A plasma can behave like a fluid, a gas, and an electrical circuit at the same time. It supports waves, currents, and instabilities that feed on pressure gradients. The very conditions needed for fusion create energy that can disturb confinement. A steep difference between the hot center and cooler edge contains stored energy, and nature tends to flatten such differences. Turbulence forms small swirling structures that carry heat outward. These structures may be tiny compared with the machine, yet together they determine whether the plasma remains hot or quickly cools. Engineers cannot eliminate every fluctuation. They must shape fields, heating methods, and plasma geometry so that fluctuations remain tolerable. Heating the plasma is itself a layered task. Passing current through it produces resistive heating, much as current heats a wire, but plasma becomes less resistive as it grows hotter. Electrical current is useful during startup, yet becomes less effective near fusion conditions. Additional energy must come from other methods. Neutral beam injection accelerates atoms to high speed and fires them into the plasma. Because they are neutral during entry, magnetic fields do not immediately deflect them. Once inside, collisions strip away their electrons, turning them into charged particles that become trapped and transfer energy to the fuel. Radio frequency heating uses electromagnetic waves tuned to motions within the plasma. These waves can transfer energy to ions or electrons, much as a timed push increases the motion of a swing. Each heating system adds complexity, consumes power, and must deliver energy through or around the reactor wall without introducing impurities. The plasma is not heated once and left alone. It continually loses energy through radiation, particle escape, turbulence, and contact at the edge. Heating must compensate until fusion reactions provide enough self-heating to reduce the external demand. Even then, control remains delicate because too much pressure can destabilize the magnetic configuration. The reactor seeks a state in which the plasma is energetic enough to fuse, but not so energetic in the wrong patterns that it disrupts itself. The wall remains present even when the core is magnetically suspended. At the outer edge, particles and heat must eventually be removed. A tokamak commonly uses a diverter, positioned where carefully guided field lines carry escaping particles away from the main chamber. The diverter acts as an exhaust system. It collects helium produced by fusion, controls impurities, and handles intense heat flowing from the plasma edge. In future power plants, the heat concentrated on diverter surfaces may approach levels faced by spacecraft during atmospheric entry, but it must be handled repeatedly or continuously. Materials such as tungsten are considered because they tolerate high temperatures and resist erosion better than many alternatives. Yet no material is invulnerable. Bombardment can knock atoms from the surface, and those atoms may enter the plasma. Once inside, heavy impurities radiate energy efficiently and cool the fuel. The wall can therefore poison the plasma that damages it, creating a feedback between confinement and materials. Plasma shape becomes another tool for control. A circular cross-section is simple, but elongated or triangular forms can improve stability and performance. These shapes require active magnetic control. Sensors monitor the plasma position and behavior, while coils adjust fields in response. The control system must act quickly because some instabilities grow faster than mechanical equipment can move. It must also interpret a system that is difficult to measure directly. Instruments examine emitted light, magnetic signals, particles, and radiation to infer temperature, density, current, and internal motion. Many important properties are reconstructed from indirect evidence. Modern control increasingly depends on detailed simulations and rapid computation, yet models must account for processes spanning enormous differences in scale. Electron motion occurs over tiny distances and brief times, while the reactor operates across meters and much longer intervals. Calculating every particle is impossible, so scientists use approximations, fluid descriptions, statistical methods, and reduced models. The challenge is to predict enough of the plasma's response to prevent damaging events. Among the most serious is a disruption, a sudden loss of confinement in which the plasma cools rapidly and its current collapses. The stored magnetic and thermal energy must go somewhere. It can produce strong mechanical forces, intense heat loads, and fast electrons that strike the wall. Avoiding disruptions, detecting their approach, and reducing their consequences are essential for a practical tokamak. A laboratory machine can pause after a severe event. A power station cannot depend on frequent recovery and repair. This changes the meaning of success. A plasma that reaches impressive conditions once may demonstrate physics, but a useful reactor must reproduce those conditions with extraordinary reliability. It must start, heat, confine, exhaust, and control the plasma again and again, or sustain it continuously, while protecting the machine around it. The magnetic container must be strong but adjustable, stable but responsive, invisible but precisely known. It must confine matter that constantly seeks to cross it, cools when it escapes, and damages whatever receives it. Fusion plasma is not merely hot gas suspended in a field. It is a dynamic electrical environment whose behavior emerges from countless particles acting together. Holding it requires a balance between force and motion, structure and instability, heating and loss. The reactor walls remain only a short distance away, cold enough to destroy fusion conditions and vulnerable enough to be destroyed by them. Between the two lies a thin magnetic boundary, never perfect, always under pressure, carrying the impossible task of keeping a star from touching its cage. Fusion is often described as a problem of temperature, as though the reactor succeeds once the fuel becomes hot enough. Temperature matters because it raises particle speeds and increases the chance that nuclei can approach closely enough to fuse. Yet temperature by itself says little about whether a plasma can produce useful power. A thin cloud of energetic particles may be very hot while generating almost no fusion. A dense plasma may contain many possible collisions but lose its energy before enough reactions occur. A long-lived plasma may remain stable while still being too cool or too sparse to matter. Practical fusion requires three conditions to overlap: temperature, density, and confinement time. Together they define whether the fuel can release energy faster than the system loses it. This relationship is expressed through the Lawson criterion, a framework that compares the rate of fusion heating with the rate of energy loss. In its simplest form, the criterion asks whether the product of particle density and energy confinement time becomes large enough at a given temperature. A related measure, called the triple product, includes temperature directly. The result is not a universal number but a boundary that changes with the fuel and reactor concept. Below that boundary, the plasma cools unless outside systems keep supplying more energy than fusion returns. Above it, fusion heating can become strong enough to support the plasma and move toward ignition. Density determines how often nuclei encounter one another. If the number of particles in a volume doubles, the chance of collision rises by more than a simple doubling because each nucleus has more possible partners. Fusion power therefore grows roughly with the square of density for a plasma containing suitable proportions of two fuels. A denser plasma can therefore produce far more reactions in the same space. Yet density cannot be increased without limit. In magnetic confinement machines, higher plasma pressure pushes harder against the magnetic field. If that pressure grows too large relative to the magnetic pressure, the plasma becomes more difficult to stabilize. Stronger magnets can help, but magnets have limits set by materials, cooling systems, mechanical stresses, and cost. The plasma also becomes harder to heat evenly as density rises, and some radiation losses increase. More particles mean more collisions, but they also create more ways for energy to move outward. Confinement time describes how long the plasma keeps its energy before losing it. It does not mean that every particle remains trapped for exactly that period, since some escape quickly while others circulate much longer. The energy confinement time is a broad measure of how rapidly the plasma's stored thermal energy would disappear if heating stopped. A long confinement time gives nuclei repeated opportunities to collide. It also allows energy from fusion products to remain in the plasma and warm the fuel, but extending confinement is difficult because plasma naturally develops turbulence, waves, drifts, and instabilities. Even when the average magnetic geometry is closed, microscopic motion carries heat across magnetic surfaces. The reactor can resemble a vessel with no visible holes and still leak energy through collective behavior. Temperature, density, and confinement time therefore act less like separate targets and more like a trade. If one is lower, another must rise to compensate. Magnetic confinement devices usually operate with relatively low density and aim for long confinement. Inertial confinement experiments take the opposite route. They compress a small fuel capsule to enormous density for an extremely brief moment. the fuel disassembles almost immediately, but if fusion occurs fast enough before that expansion, the short confinement can be balanced by the extraordinary density. One holds plasma for extended periods while the other creates a tiny compression event, yet both attempt to cross the same threshold. They choose different positions on the same map of temperature, density, and time. In a tokamak, reaching a high triple product requires more than heating the core. The plasma must be large enough and well insulated enough that its interior does not lose energy too quickly through the edge. Larger devices often confine heat better because the hot volume grows faster than the surface through which energy escapes. This helps explain why major tokamaks become enormous. Size can improve the physical balance. A larger plasma has more room for a hot central region separated from material walls, and it can retain energy longer. Yet scale brings heavier structures, stronger forces, costly magnets, and difficult maintenance. The physical route toward improved confinement can lead directly into an economic challenge. Smaller machines promise lower cost and faster construction, but they may need stronger magnetic fields, more advanced materials, or different confinement concepts to compensate for reduced size. The temperature itself also has an optimum range. At low temperature, few nuclei fuse because the Coulomb barrier remains difficult to penetrate. As the plasma grows hotter, the reaction rate rises sharply. Beyond a certain region, however, additional temperature brings diminishing returns for some fuel cycles. Faster particles may spend less time near one another during collisions, while radiation and transport losses continue. The reactor does not seek unlimited heat. It seeks a region where the fusion reaction is probable enough. Self-heating is effective, and losses remain controllable. For deuterium and tritium, this useful range is far beyond ordinary material temperatures but still lower than what many advanced fuel reactions require. That relative accessibility is why deuterium-tritium fusion remains the leading path despite the neutron damage and tritium problems it creates. Fusion gain is another idea shaped by where the boundary is drawn. A gain factor often compares fusion power with power delivered to the plasma. If the fusion output equals the external heating power, the plasma reaches scientific break-even under that definition. But the facility may still consume much more energy than the plasma receives because heating systems are not perfectly efficient. Electricity may first power radio frequency generators, neutral beam systems, magnets, pumps, and cryogenic equipment. Only part of that electricity reaches the fuel. A plasma gain above 1 is therefore an important physics milestone without being a complete power plant milestone. Engineering break-even requires the fusion system to recover enough energy to operate its own supporting machinery. Commercial operation requires still more. Because a plant must deliver substantial surplus electricity while covering maintenance and capital costs. Ignition sits further along the physics scale. In an ignited deuterium-tritium plasma, charged helium products deposit enough energy to maintain fusion temperature without continuous external heating. The neutrons escape, but the helium nuclei remain confined long enough to warm the surrounding fuel. This creates a positive feedback. More fusion produces more helium heating, which supports more fusion. That feedback also demands control. A burning plasma is not passive. Its internal heat source responds to changing conditions. If density, temperature, or impurity levels shift, the reaction rate can change rapidly. Control systems must regulate fueling, exhaust, magnetic shape, and radiative cooling so that the plasma stays near a desired operating point. Too little self-heating causes the reaction to fade. Too much localized heating can steepen pressure gradients and trigger instability. Success is not simply starting the fire, but governing it. Impurities complicate the triple product because they occupy space and interact with the plasma, without contributing equally to fusion. Helium ash is unavoidable. Each deuterium-tritium reaction leaves a helium nucleus behind, and that helium must eventually be removed. While newly created helium helps heat the plasma, cooled helium dilutes the fuel. If ash accumulates, fewer deuterium and tritium nuclei remain in the same volume, and fusion power falls. Atoms eroded from the walls can be even more damaging. Heavy elements radiate strongly when their electrons change energy states, draining heat from the plasma. A temperature measurement may remain impressive at the center, while the overall energy balance deteriorates because the edges are radiating power away. The reactor must therefore fuel and clean itself at the same time. Adding fresh isotopes while exhausting helium and impurities without disrupting confinement. The narrowness of the operating window explains why records in fusion research often emphasize different achievements. One machine reaches exceptional temperature. Another holds plasma for an unusually long period. Another produces a high fusion yield during a brief pulse. Each result advances one part of the triple product, but the full challenge is their combination. A power plant must reach the required balance repeatedly or continuously, with systems that survive the resulting heat and neutron flow. Temperature is the most dramatic condition because it evokes the interior of a star. But density and time quietly decide whether that heat becomes useful. Fusion remains difficult because the plasma must be hot enough for rare nuclear encounters, crowded enough for those encounters to occur in great numbers, and patient enough to keep its energy before the outside world takes it away. None of these demands stands alone. Each pushes against the others, forming a narrow corridor through which every successful reactor must pass. The two most developed magnetic paths toward fusion begin with the same basic idea and then separate in the way they create order. Both the tokamak and the stellarator try to hold a ring of hot plasma inside a magnetic cage, keeping charged particles away from solid walls while preserving enough heat and density for fusion. Both use powerful coils, carefully shaped chambers, vacuum systems, heating equipment, diagnostics, and active control. Yet the geometry of their magnetic fields is built by different means, and that difference reaches into nearly every question of stability, efficiency, maintenance, and operation. The tokamak became the dominant design because it offered comparatively strong confinement with a magnetic structure that could be understood and built using simpler coil shapes. Its chamber forms a torus, and external magnets create a field that circles the long way around the ring. This field alone is not enough. Particles would drift because the magnetic strength changes across the curved chamber. The tokamak therefore drives a large electrical current through the plasma itself. That current creates a second magnetic field around the short direction of the torus. Combined, the two fields twist into helical paths, guiding particles around both the inner and outer sides of the machine and reducing their tendency to drift outward. The plasma becomes not only the fuel but also part of the magnet. This arrangement produces elegant physics, but it carries a built-in weakness. The current is difficult to sustain indefinitely. In many tokamaks, it is induced by a central transformer, which works in pulses. A changing magnetic field drives current in the plasma in much the same way that a transformer drives current through a secondary circuit. Once the magnetic swing reaches its limit, the pulse must end or other methods must take over. Auxiliary techniques can drive current using radio waves or injected particles, and some tokamak designs aim for long or continuous operation, but maintaining the current consumes power and introduces new control problems. The current also stores energy and can become unstable. If it changes too quickly, the plasma may suffer a disruption, losing confinement and depositing energy into the surrounding structure. The strength of the tokamak is therefore tied to one of its greatest risks. The same current that helps create good confinement can trigger sudden events when the plasma slips outside its stable operating range. Tokamak research has spent decades learning to shape, heat, fuel, and control this current-carrying plasma. The magnetic geometry can be adjusted by external coils, producing elongated or triangular cross-sections that improve performance. Feedback systems watch the plasma position and respond with rapid corrections. Operating regimes have been discovered in which turbulence near the edge is reduced and confinement improves. One of the most important is the high confinement mode, in which a transport barrier forms near the plasma boundary. Heat remains trapped more effectively, allowing higher pressure and stronger fusion performance. Yet the barrier can also create steep pressure gradients that lead to periodic bursts at the edge. These events can throw heat and particles toward the walls. A state that improves overall confinement may therefore intensify local damage. The tokamak repeatedly reveals this pattern. Progress in one measure creates pressure elsewhere. The stellarator avoids the need for a large plasma current by building the twist directly into the external magnetic field. Its coils are shaped in complex three-dimensional curves, producing a magnetic path that winds around the torus without relying on the plasma to generate the essential twist. In principle, this allows steady operation. There is no transformer pulse that must naturally end, and the risk of major current-driven disruptions can be reduced. A stellarator can behave more like a continuously operating magnetic bottle, which is attractive for a power station expected to run for long periods. Yet the price of that advantage is geometric complexity. Instead of comparatively regular coils arranged around a symmetric torus, the stellarator uses coils whose surfaces bend and twist with remarkable precision. Small manufacturing errors can distort the field. The chamber, supports, heating systems, diagnostics, and maintenance equipment must fit around irregular shapes. Every opening for a sensor, fuel line, or replacement component must respect the magnetic design. Building such a machine requires advanced computation and manufacturing that did not exist when the stellarator was first proposed. Early stellarators suffered from poor confinement because particles drifted out through flaws in the magnetic geometry. Their fields looked closed in a simple drawing, but contained hidden routes that allowed particles to escape. For a time, tokamaks seemed decisively superior. The balance began to change as computers made it possible to calculate and optimize three-dimensional magnetic fields in far greater detail. Modern stellarators are designed by searching through vast families of possible shapes, reducing particle losses and tailoring the field to improve confinement. The resulting machines can be physically strange, with twisted chambers and coils resembling sculpted ribbons around an asymmetric ring. Their complexity is not decorative. Each curve exists to guide particles, balance drifts, and preserve magnetic surfaces. This makes the stellarator less dependent on plasma current but more dependent on exact construction. Tokamaks and stellarators therefore exchange one kind of difficulty for another. The tokamak places more of the magnetic task inside the plasma, giving it strong performance but creating sensitivity to current and disruptions. The stellarator places more of the task in the external structure, offering steadier operation but demanding intricate design and fabrication. Neither approach removes turbulence. Even a perfectly shaped magnetic field cannot prevent all microscopic transport. Collisions, waves, and small instabilities still carry energy outward. Both machines must manage impurities, helium ash, heat exhaust, neutron damage, and the intense burden placed on plasma-facing components. Both must fit breeding blankets and cooling systems around magnets that need shielding. Both must provide access for remote maintenance in spaces already crowded with coils and support structures. The difference in field creation changes how these problems appear, but it does not make them disappear. Their operational rhythms also differ. A pulsed tokamak may expose structures to repeated heating and cooling, creating fatigue as components expand and contract. A steady stellarator could avoid part of that cycling, but continuous operation would demand equally continuous exhaust, fueling, tritium handling, and heat removal. Stability over hours does not reduce the need for durability over years. Size also affects both designs. Larger machines generally improve confinement, but they increase cost and complicate construction. Stronger magnetic fields can allow more compact reactors, yet the magnets must withstand immense forces. Superconducting materials reduce electrical losses, but they require cryogenic cooling and protection from neutron radiation. A fusion device therefore contains extreme side-by-side plasma at temperatures beyond the solar core and magnets maintained near absolute zero. Between them lie shields, vacuum vessels, structural metals, and narrow tolerances. The machine must preserve both environments without allowing either to destroy the other. In a tokamak, the need for current drive and disruption control adds to this burden. In a stellarator, the twisted coils and limited maintenance access add different burdens. The choice between them is not simply a contest over which shape confines plasma better. It is a contest over which complete system can become a practical power plant. Tokamaks hold the advantage of a larger experimental history, a broad international research base, and decades of operational knowledge. Many of the largest fusion projects use the tokamak design because its performance is better mapped and its path toward burning plasma has been studied in depth. Stellarators offer the possibility of long-duration stability and lower disruption risk, qualities that may become more valuable as fusion moves from experiments toward electricity generation. Their modern progress shows that the old disadvantages are not fixed, but their engineering remains demanding. The future may not belong exclusively to either design. Improvements in magnets, control systems, materials, and computation may reshape both. Hybrid concepts may borrow features from each. What remains constant is the central trade. Magnetic confinement requires a twist, and that twist must come either from the plasma, from the machine, or from some combination of both. The tokamak asks a living, unstable plasma to help build its own cage. The stellarator carves that cage into metal before the plasma arrives. One is simpler in outline but harder to govern from within. The other is calmer in principle but difficult to build from without. Both reveal why fusion resists a single elegant solution. The field that protects the plasma must itself become an extraordinary machine, precise enough to guide particles for long periods and robust enough to survive the energy that successful fusion would release. A magnetically confined plasma can appear calm from a distance, glowing inside a carefully shaped chamber while coils hold it away from the walls. Yet its interior is never truly quiet. Individual ions spiral around magnetic field lines. Electrons move even faster. Currents shift. Waves travel. And pressure changes from the hot center to the cooler edge. These motions interact until the plasma develops turbulence, a restless state in which small disturbances grow, merge, break apart, and carry energy outward. Turbulence is one of the most persistent reasons fusion remains difficult, because it drains heat from the very region where fusion must occur. A reactor may create the correct temperature and density, but if turbulent transport moves energy to the edge too quickly, the core cools before enough nuclei can fuse. The plasma instead finds microscopic routes across the field, creating a leak without a physical crack. In an idealized magnetic field, charged particles follow orderly paths. They circle field lines and move along them, remaining tied to nested magnetic surfaces inside the reactor. Real plasmas are more complicated. Magnetic fields curve and vary in strength. Particles collide. Electric fields arise from small separations of charge. The plasma pressure is far higher in the core than near the wall, creating a strong gradient. Gradients store free energy, and free energy can feed instability. Any small fluctuation in density, temperature, or electric potential can draw power from that gradient. The fluctuation grows, bends particle paths, and creates swirling structures that move heat and matter across the confining field. This process resembles turbulence in air or water, but plasma turbulence includes electric currents and magnetic forces, making it far more complex than ordinary fluid motion. One important family of disturbances is driven by differences in temperature and density across the plasma. A tiny region becomes slightly hotter or denser than its surroundings. That difference alters local electric fields and particle motion. The disturbed region drifts, stretches, and breaks into structures that transport energy. These motions can form eddies that move across magnetic surfaces, even though individual particles still spiral around field lines. The plasma behaves collectively, so the motion of one charged population reshapes the fields experienced by another. This range of scales makes prediction difficult. The smallest relevant motions may occur near the orbit size of ions or electrons, while the reactor as a whole evolves over much larger distances and longer times. A complete calculation would have to follow an immense number of particles and their self-generated fields at once. Even powerful computers cannot reproduce every detail of a reactor plasma over full operating periods. Scientists therefore use reduced models, statistical descriptions, and simulations that focus on selected scales. These tools reveal patterns, but turbulence remains sensitive to geometry, pressure, magnetic shear, collisions, and impurities. A small change in plasma shape or heating can transform the transport. Nearly similar discharges can lose energy at different rates, because a subtle shift allows an instability to grow. Magnetic shear offers one way to resist this process. Shear means that the direction of the magnetic field changes from one surface to another. A turbulent structure trying to extend across several surfaces is twisted and pulled apart, because each layer guides it along a slightly different path. Flow shear can produce a similar effect when adjacent layers of plasma move at different speeds. Eddies become stretched until they can no longer transport heat efficiently. This helps explain why certain operating regimes suddenly achieve better confinement. Under the right conditions, a barrier forms near the plasma edge, reducing turbulent transport and allowing the interior pressure to rise. The transition can be abrupt. A plasma that had been leaking heat steadily enters a new state in which the edge becomes more organized, and the core grows hotter. This high confinement state is valuable because it brings fusion conditions closer without requiring a proportional increase in heating power. Yet it creates another difficulty. The same barrier that holds heat inside also steepens the pressure gradient near the edge. Energy accumulates behind it. Eventually, the edge can become unstable and release bursts of particles and heat toward the wall. These events, often called edge-localized modes, can repeat in pulses. In a power reactor, each burst could place damaging stress on plasma-facing materials. A solution that improves global confinement can therefore intensify local erosion. Researchers explore magnetic adjustments, particle injection, and alternative regimes, but each method affects density, temperature, exhaust, and stability. The plasma must be quiet enough to preserve heat but active enough to release ash and impurities. Perfect confinement would not be desirable if helium produced by fusion could not escape. Turbulence is therefore not simply an enemy to be eliminated. Some transport is necessary. Fresh fuel must reach the core, helium ash must move outward, and excess heat must be guided toward the exhaust system. The goal is selective transport slow enough in the core to support fusion, controlled enough at the edge to protect the walls, and sufficient enough to remove waste. Nature does not naturally divide these roles. The same turbulent processes that carry helium outward may also carry valuable heat with it. Suppressing one pathway can trap impurities, enhancing another can cool the plasma. Reactor operation becomes an attempt to shape a living flow rather than seal a static container. Large-scale instabilities add another layer of risk. Some are connected to the plasma current, some to pressure, and some to the shape of the magnetic field. A slight displacement may cause the entire plasma column to move vertically. A twisting disturbance can rearrange internal magnetic surfaces. Small magnetic islands can form where field lines reconnect, creating regions that flatten temperature and pressure. If these islands grow, confinement deteriorates. In a tokamak, certain instabilities can lead to a disruption, a rapid collapse of the plasma current and stored energy. A local disturbance may spread as magnetic structure breaks and reforms. Heat reaches the wall in a short pulse. Electrical currents appear in surrounding metal. Mechanical forces rise. In severe cases, electrons can be accelerated to extremely high energies and strike the vessel. A commercial reactor must either avoid such events with exceptional reliability or reduce them before they become destructive. Avoidance depends on prediction, and prediction depends on understanding signals that may be weak, ambiguous, or specific to each plasma state. Diagnostics measure magnetic fluctuations, radiation, density, temperature, and particle emission. Control systems search for patterns that suggest an instability is growing. Modern experiments increasingly use machine learning to recognize warning signs across large data sets. But recognition is not the same as physical certainty. A warning may arrive too late, or a control action may disturb another part of the plasma. The system must decide within fractions of a second whether to adjust coils, alter heating, inject material, or deliberately shut the plasma down in a controlled way. Control is difficult because the plasma changes as it is measured. Heating modifies currents, fueling modifies density, magnetic corrections modify shape. Every action becomes part of the next instability. Turbulence also complicates the path from one machine to another. Plasma behavior does not scale in a simple way. A larger reactor may retain heat better, but it may also enter regimes that smaller devices cannot fully reproduce. Stronger magnetic fields can reduce some losses while increasing mechanical and engineering demands. Experimental scaling laws offer guidance, yet remain uncertain when extended to new sizes and power levels. A future burning plasma adds self-heating from fusion products, creating conditions that present reactors can only partly imitate. The turbulence will then respond not just to external heaters, but to energetic helium nuclei born throughout the core. Their motion can excite new waves and redistribute energy. The plasma becomes more self-organized and less dependent on direct external control, which is necessary for efficient power generation, but makes its behavior harder to command. The magnetic field may define the cage, but turbulence decides how porous that cage becomes. It operates in the narrow space between order and disorder, drawing energy from the gradients that fusion requires. A reactor needs a hot center, a cooler edge, strong pressure, flowing particles, and intense currents. Each of these conditions can feed instability. The machine must preserve the gradients without allowing them to break into destructive motion. This is why a stable-looking plasma can still fail its energy balance. The glow remains inside the chamber, the magnets continue to function, and yet heat quietly slips outward through invisible eddies. Fusion does not end only in spectacular disruptions. It can also fade through countless small losses, each too subtle to see, together strong enough to keep the star from sustaining itself. Among the many reactions that can release energy through fusion, deuterium and tritium remain the leading choice because they offer the most practical route through the nuclear barrier. They are not ideal fuels in every sense. Tritium is scarce, radioactive, and difficult to handle. Their reaction releases a fast neutron that cannot be confined by magnets and gradually damages the reactor around it. Yet compared with other possible fuel cycles, deuterium and tritium fuse at lower temperatures and with much greater probability. In a field where every increase in temperature, pressure, and confinement creates new engineering burdens, that advantage is decisive. The reaction does not remove the difficulty of fusion. It reduces the first difficulty enough for the remaining ones to become visible. Deuterium is a stable isotope of hydrogen. Its nucleus contains one proton and one neutron, while ordinary hydrogen contains only a proton chemically. The two behave almost identically because chemistry depends mainly on electrons, but the extra neutron changes the nuclear possibilities. Deuterium occurs naturally in water in small but useful amounts. It can be separated from ordinary hydrogen through industrial processes that exploit slight differences in mass and physical behavior. The oceans therefore hold an enormous reserve. A commercial fusion economy would not face an immediate shortage of deuterium, and the fuel could be obtained by countries without access to fossil deposits or uranium mines. This abundance helps give fusion its reputation as a nearly limitless energy source, though abundance in nature does not guarantee simplicity inside a reactor. Deuterium must still be purified, stored, injected, recovered, and processed as part of a closed fuel system. Tritium is another isotope of hydrogen, containing one proton and two neutrons. Unlike deuterium, it is unstable. It undergoes radioactive decay and has a half-life of a little more than 12 years, meaning that any stored quantity gradually disappears. Natural production is extremely limited because tritium does not survive for geological periods. Small amounts form in the upper atmosphere when cosmic rays interact with gases, but this source is far too small for power generation. Existing supplies come mainly from certain fission reactors, where neutrons interact with materials containing lithium or heavy water. The total accessible inventory is measured in only tens of kilograms, a remarkably small amount for a fuel expected to support a global industry. A single large fusion program could consume a significant fraction of what currently exists if it operated for long. This makes tritium less like a conventional commodity and more like a seed stock. Early reactors must begin with enough of it to operate, then breed additional fuel from lithium using the neutrons released by fusion. The attraction of the deuterium-tritium reaction lies in its nuclear cross-section, a measure of how likely a reaction is to occur when particles meet at a given energy. This cross-section rises to useful values at temperatures lower than those needed by most competing fusion fuels. Lower is relative. The plasma still must reach temperatures of many millions of degrees, yet a reactor using only deuterium, or deuterium with helium-3, would generally require much hotter conditions or achieve lower reaction rates at the same temperature. Every additional demand on temperature increases losses, stresses magnetic confinement, and raises the challenge of heating. Deuterium and tritium therefore offer the widest margin within a narrow field of possibility. When their nuclei fuse, they form a helium-4 nucleus and release one neutron. The helium nucleus carries a smaller share of the energy and remains electrically charged, so magnetic fields can keep it inside the plasma for a time. As it slows through collisions, it transfers energy to the surrounding fuel. This internal heating is essential for a burning plasma. The neutron carries most of the energy and leaves the magnetic cage almost immediately, because it has no electric charge. It travels outward into the blanket, where its motion can become heat, and where it may also help produce new tritium from lithium. The reaction therefore divides its energy into two roles. The helium supports the fire from within, while the neutron carries usable power to the machine around it. This division is both helpful and troublesome. The neutron makes heat extraction possible without placing pipes inside the plasma, but it also carries destructive energy into every structure it reaches. It can knock atoms from their positions, alter chemical elements, weaken materials, and activate components. A reaction chosen because it is easiest to ignite creates one of the hardest materials environments ever engineered. Alternative fuels appear attractive because some produce fewer neutrons or release more of their energy in charged particles. Deuterium can fuse with another deuterium nucleus through more than one branch, creating either tritium and a proton or helium-3 and a neutron. This avoids dependence on an initial tritium supply, but the reaction rate is lower at comparable temperatures, and neutrons are still produced. The tritium created in one branch can later fuse with deuterium, so a deuterium reactor would not be truly neutron-free. It would also need hotter plasma and stronger confinement, reducing the apparent simplicity of using a single abundant fuel. Deuterium and helium-3 can produce helium-4 and a proton, with most energy carried by charged particles. In principle, those charged products could allow more direct conversion of energy into electricity and reduce neutron damage. Yet helium-3 is rare on Earth, and the reaction requires more demanding plasma conditions. Side reactions involving deuterium would still produce neutrons. Proton-boron fusion is often presented as an even cleaner possibility because its main reaction yields charged helium nuclei and very few direct neutrons. But boron carries a higher positive charge than hydrogen, making the electromagnetic barrier much harder to cross. The plasma must become far hotter, and radiation losses from electrons become severe. A fuel cycle that looks elegant in its final products may be much harder to sustain in its initial state. Deuterium-tritium fusion survives comparison because it asks the least impossible question first. Its disadvantages come after the reaction begins, while many alternative fuels struggle to reach a useful reaction rate at all. This does not mean that future fusion will always use deuterium and tritium. Better magnets, improved confinement, direct energy conversion, or new plasma concepts may make advanced fuels more realistic. Early commercial reactors, however, must work with existing physics and engineering margins. They need a fuel whose probability of fusion is high enough to compensate for imperfect confinement and unavoidable losses. Deuterium and tritium provide that chance. Their use also shapes the entire reactor. Fueling systems must inject hydrogen isotopes without cooling the plasma excessively. Some designs use gas, while others fire frozen pellets deep into the hot core. The fuel does not remain neatly separated from the exhaust. Deuterium, tritium, helium ash, and impurities circulate through pumps and processing equipment. Tritium can diffuse into metals, become trapped in surfaces, and escape through tiny leaks. Because it is radioactive and chemically behaves like hydrogen, it can enter water and spread through systems that would not contain heavier elements in the same way. A power plant must account for nearly every gram, recover it from exhaust, remove impurities and return it to the plasma, inventory held in pipes. Pumps, blankets, and walls may be as important as the amount actively burning. The reactor, therefore, becomes a chemical processing plant wrapped around a nuclear plasma. Tritium's decay adds further pressure. A reserve cannot simply be stored for generations. It must be used, replenished, and protected from loss. The startup of a fusion industry creates a difficult sequence because each new reactor needs an initial charge before it can breed its own fuel. If early plants consume more tritium than they produce, expansion slows or stops. A breeding blanket must therefore achieve more than theoretical replacement. It needs a margin above unity to cover decay, processing losses, reserve requirements, and fuel tied up elsewhere in the system. That margin is difficult because not every neutron reaches lithium, and some are absorbed by structural materials or lost through openings. The same neutron must help breed fuel, produce heat, and protect sensitive magnets through carefully arranged layers. Choosing deuterium and tritium solves the reaction probability problem only by transferring difficulty into fuel management, blankets, and materials. Their dominance is not proof that they are perfect. It is evidence of how unforgiving fusion physics remains. The easiest available reaction still demands a plasma hotter than any solid can touch, a radioactive fuel that barely exists in nature, and a neutron environment that steadily changes the machine. Yet this combination offers the clearest path toward a self-heating plasma. Deuterium supplies abundance, tritium supplies reactivity, helium carries heat back into the fuel, and neutrons carry energy outward. In that carefully balanced exchange lies both the reason this fuel cycle leads and the reason fusion power remains unfinished. The fuel cycle of deuterium and tritium contains a hidden limit that becomes more severe as fusion approaches practical scale. Deuterium is widely available, but tritium is not. It exists only in tiny quantities, decays steadily, and cannot be mined from a natural reserve large enough to support power stations. A future reactor must therefore create its own tritium while it operates. Fusion becomes not merely a machine that burns fuel, but one that must reproduce part of its supply with enough margin to cover decay, leakage, processing delays, and inventory held throughout the plant. If breeding falls even slightly short, operation slowly consumes the available stock. A reactor may achieve excellent plasma performance and still fail because it cannot feed itself. Tritium's scarcity begins with its instability. Its nucleus contains 1 proton and 2 neutrons, a combination that does not remain unchanged forever. Through radioactive decay, 1 neutron transforms, and the tritium becomes helium-3. The half-life is a little more than 12 years, so a stored reserve loses fuel even when no reactor is running. This makes stockpiling difficult. Uranium can remain available for immense periods, but tritium behaves more like a perishable resource. Every year removes part of the inventory, and delays in reactor construction consume fuel before a plant begins operation. Existing tritium is produced mainly as a byproduct in certain fission systems. Heavy water reactors can generate it when neutrons interact with deuterium in the moderator, and specialized reactors can produce it through lithium-bearing targets. These sources are limited, expensive, and tied to technologies that may not expand with fusion. The global amount available outside weapons programs is small, and much is already committed elsewhere. A fusion economy cannot assume that fission reactors will supply fuel indefinitely, even if existing production continues. It remains far below what a fleet of power plants would consume. This creates a startup problem. The first generation of fusion machines needs tritium before its own breeding systems are proven. Each reactor requires a working inventory not only in the plasma, but also in storage vessels, pumps, pipes, processing units, and the blanket. Tritium moves through the plant, and some becomes trapped in materials. The amount circulating outside the plasma can exceed the amount burning at any moment. A new reactor may therefore need kilograms of initial inventory, even though each event consumes almost nothing. When many plants are planned, the startup stock becomes a strategic constraint. One reactor cannot merely breed enough for itself if the wider industry also needs fuel for new machines. It must produce a surplus. Breeding begins with lithium. When a fusion neutron enters the blanket surrounding the plasma and strikes certain lithium nuclei, a nuclear reaction can produce tritium and helium. Lithium-6 is especially useful because it can breed tritium, even with relatively low-energy neutrons. While lithium-7 contributes under different conditions and higher neutron energies. The basic idea appears simple. The escaping neutron creates fuel that later returns, yet the neutron has many competing destinations. Some are absorbed by structural metals, coolants, shielding, and diagnostic ports. Some escape through openings. Some scatter and lose energy before reaching useful lithium. The blanket must direct enough neutrons into breeding material while still allowing heat removal, maintenance access, and protection of the magnets. This balance is measured by the tritium breeding ratio, which compares the amount produced with the amount consumed. A ratio of exactly 1 appears sufficient only in an ideal system. Real plants require more. Tritium decays. Some is lost during extraction and processing. Some remains trapped in walls or blanket materials. Some must be held in reserve for interruptions and restart. The plant also needs time to remove newly bred tritium, clean it, and return it to the fuel cycle. During that delay, more fuel is consumed. A practical reactor therefore needs a breeding margin above unity, and the exact margin depends on every supporting system. Achieving it is harder than a simple nuclear calculation suggests because the blanket cannot be optimized for breeding alone. It also receives most of the fusion energy, so it must convert neutron motion into heat and transport that heat into a coolant. It must shield superconducting magnets, survive mechanical and thermal stress, resist corrosion, and remain compatible with tritium extraction. A material that breeds well may conduct heat poorly. A coolant that removes heat efficiently may absorb too many neutrons. A strong structural alloy may interfere with breeding. Every support, channel, joint, an opening changes the neutron economy. A few percent lost in one region can decide whether the plant produces surplus fuel or slowly runs out. Neutron multipliers may improve the balance. Materials such as beryllium or lead can release additional neutrons when struck by energetic fusion neutrons. These extra particles increase the chance that lithium reactions occur, helping compensate for losses. Yet multipliers bring costs. Beryllium is scarce, toxic as dust, and vulnerable to damage. Lead is heavy, corrosive in some systems, and difficult to circulate at high temperature. Both can become activated by neutron exposure. Their use reflects the recurring structure of fusion engineering. A material introduced to solve one shortage becomes another source of complexity. Blanket concepts vary widely. Some use solid ceramic compounds containing lithium, arranged in pebbles or blocks with a separate coolant. Others use liquid metals or molten salts that contain lithium and can serve as both breeder and coolant. Solid breeders may be easier to confine, but tritium must diffuse out of the material and enter a collection stream. Radiation damage and thermal cycling can crack or alter the ceramic. Liquid breeders can move heat and tritium through the system, but they interact with strong magnetic fields, corrode structures, and create difficult fluid behavior. A conducting liquid moving through a magnetic field experiences forces that resist its motion and alter its flow. Pumping can become harder, pressure can rise, and heat transfer can change. No blanket escapes trade-offs between nuclear performance, thermal efficiency, chemistry, magnetism, safety, and maintenance. Tritium must be extracted quickly because it should not remain inside the blanket longer than necessary. It behaves chemically like hydrogen and can diffuse through metals, dissolve in liquids. An exchange with ordinary hydrogen in water, it may become trapped at defects created by neutron damage. A plant must separate it from breeder materials, purify it, measure it, and return it to the fueling system. Each step occurs inside controlled equipment because tritium is radioactive and easily dispersed. Its beta radiation is weak and cannot penetrate skin deeply, but tritium becomes more concerning when inhaled, swallowed, or incorporated into water. Containment therefore depends on multiple barriers, continuous monitoring, and recovery systems. The small size of hydrogen isotopes makes perfect sealing difficult. Tritium can pass through materials that would easily contain larger molecules. Inventory accounting becomes part of reactor physics. Operators must know where the tritium is, how much is moving, how much is trapped, and how much has been bred. Uncertainty cannot be large because the stock is precious and safety limits restrict accumulation. A reactor that loses only a small percentage during each cycle may appear efficient, yet over time that loss can consume the breeding margin. Recovery and measurement must therefore reach levels rarely required in ordinary power plants. Tritium scarcity also links the pace of fusion development to the success of early breeders. A demonstration plant that consumes more tritium than it produces may still prove valuable physics, but it cannot support rapid expansion. If each new reactor depends on fuel taken from a shrinking reserve, the industry grows slowly or not at all. A self-sustaining plant must replace its own consumption, and a growing fleet must collectively produce enough surplus to start additional plants. This turns breeding performance into a question of time. A small surplus may require years to accumulate startup inventory for another reactor. A larger surplus speeds expansion but demands a better neutron economy and more efficient processing. The first commercial designs therefore carry an obligation beyond generating electricity. They must become parents to the next generation of machines. This is why tritium cannot be postponed until after plasma success. The blanket must be tested under realistic neutron conditions. Yet no existing magnetic fusion device produces the same continuous intensity expected in a power plant. Experiments and simulations provide partial knowledge, but full behavior emerges only when breeding, heat removal, radiation damage, extraction, and maintenance operate together. The reactor must prove a closed fuel cycle under the same conditions that steadily degrade the components performing it. Tritium reveals the deeper meaning of fusion difficulty. The fuel is not simply placed into a chamber and burned. One isotope must be made from another element by neutrons created in the reaction, recovered from a hostile blanket, purified through complex equipment, and returned before reserves decline. The process must produce slightly more than it consumes, every day, for years. In that narrow surplus lies the difference between a brilliant experiment and an energy source capable of reproducing itself. The blanket surrounding a fusion plasma is often drawn as a simple layer between the burning fuel and the outer machine. Yet in a practical reactor, it becomes one of the most burdened components ever conceived. It must intercept the fast neutrons that escape the plasma, convert their motion into heat, breed new tritium from lithium, protect superconducting magnets, support coolant channels, resist corrosion, tolerate mechanical stress, and remain serviceable after years of radiation damage. Each task is difficult on its own. The blanket must perform all of them at once, inside a limited thickness, without absorbing so many neutrons that fuel breeding fails or retaining so much heat that materials weaken. It stands between a plasma too hot for any solid to touch and magnets that must remain extremely cold. The whole power plant depends on this region because most of the fusion energy passes through it. In deuterium-tritium fusion, the neutron leaves the reaction carrying most of the released energy. Unlike the charged helium nucleus, it does not follow magnetic field lines. It travels outward in a nearly straight path until it strikes matter. The blanket is designed to receive that impact. As neutrons collide with atomic nuclei, they slow down and transfer kinetic energy into the material. Countless microscopic collisions become heat, and that heat must be removed by a coolant before it damages the structure. The basic electricity cycle then resembles other thermal power stations. The coolant carries energy away. A heat exchanger may create steam or drive another working fluid, and a turbine produces electricity. Fusion therefore reaches for an extraordinary nuclear process, but often ends with the familiar motion of a generator. The difficulty lies in delivering heat at a useful temperature, while preserving every material between the plasma and the turbine. The same neutrons that heat the blanket must also create tritium. Lithium-bearing materials are placed where enough neutrons can reach them, but the geometry is crowded. Cooling channels occupy space. Structural supports occupy space. Openings are needed for heating beams, diagnostics, maintenance tools, vacuum pumping, and plasma control. Every region without lithium reduces breeding. Every alloy added for strength may absorb neutrons that could have produced fuel. The blanket cannot be a uniform slab because heat and neutron intensity vary around the chamber. Areas near the diverter face different loads from those around the main wall. Modules must fit into the curved interior while allowing remote replacement. Their joints must remain sealed under temperature changes, pressure, magnetic forces, and neutron damage. A tiny gap may create a local hotspot or a path for radiation to reach sensitive equipment. Neutron multiplication can improve the breeding balance. When energetic fusion neutrons strike certain materials, they can release additional neutrons. Beryllium is one candidate because it can turn one incoming neutron into more than one outgoing particle under suitable conditions. Lead can serve a related role in liquid breeder systems. These extra neutrons give the blanket more chances to perform competing tasks, such as breeding tritium while still losing some particles to structures and shielding. Yet multiplication does not create free energy. The reactions alter the materials, generate helium, and add new radiation products. Beryllium is costly, toxic when dispersed as dust, and limited in supply. Lead is dense and can be corrosive, both complicate fabrication and disposal. A solution to neutron scarcity may therefore create problems in economics, safety, and maintenance. The blanket also decides how efficiently the plant converts fusion into electricity. Thermal efficiency improves when heat is delivered at higher temperature. But high temperature intensifies corrosion, stress, and material degradation. Water cooling is well understood and can remove large amounts of heat. Yet pressurized water limits operating temperature and adds the risk of energetic reactions with some blanket materials. Helium gas is chemically inert and does not become highly activated, but it has low density and requires significant pumping power. Liquid metals and molten salts can carry heat at high temperature, but they bring magnetohydrodynamic effects, chemical reactivity, and difficult tritium control. The strongest coolant for one purpose may be the weakest for another. Pumping power matters because electricity used to circulate coolant reduces the plant's net output. A blanket that breeds fuel successfully but demands excessive auxiliary power may still fail as part of a commercial station. Liquid breeder concepts are especially attractive because the same fluid can contain lithium, capture heat, and transport tritium toward extraction systems. In principle, this combines several functions and reduces the need for separate materials. In practice, electrically conducting liquids behave strangely inside the reactor's powerful magnetic field. As the fluid moves across field lines, electrical currents are induced within it. Those currents interact with the field and create forces that resist motion, flatten velocity profiles, and increase pressure losses. Ordinary turbulence may be suppressed in some directions while new patterns develop near walls and bends. Insulating coatings can reduce electrical coupling, but coatings must survive radiation, heat, chemical attack, and repeated stress. A microscopic crack can change the flow and expose structural metal to corrosion. The blanket therefore becomes a fluid experiment inside a magnetic machine. with behavior that cannot always be reproduced at full scale before the reactor exists. Solid breeder blankets avoid some liquid flow problems by placing lithium in ceramic compounds. Small pebbles or structured blocks can release tritium when heated, while helium gas or another coolant removes energy. Yet solid materials swell, crack, sinter, and change thermal conductivity under irradiation. Tritium must diffuse through grains and pores before it can enter a collection stream. If it moves too slowly, fuel becomes trapped and the usable inventory falls. Pebble beds can settle or rearrange during thermal cycling, altering contact and heat transfer. Ceramics that breed effectively may be brittle, while structural metals that provide strength may absorb neutrons or react with the breeder. The module must accommodate expansion without losing thermal contact or creating crushing stresses. Every cycle from startup to shutdown tests these interfaces. Shielding forms another essential layer. Superconducting magnets operate at cryogenic temperature and can lose performance when exposed to heat or radiation. Neutrons that pass through the blanket can damage insulation, alter superconducting materials, and deposit energy in cold structures. Removing that heat at cryogenic temperature is especially expensive because refrigeration near absolute zero requires far more input power than removing the same heat near room temperature. The blanket and shield must therefore reduce neutron and gamma exposure to extremely low levels before it reaches the magnets. More shielding improves magnet life but adds size, weight, and cost. It may push coils farther from the plasma, weakening the magnetic field available in the core unless the magnets become stronger. A thicker protective layer can therefore demand a larger machine. The blanket influences reactor dimensions from the inside outward. Mechanical stress arrives from several directions. Coolant pressure pushes against channels and joints. Temperature differences create expansion and contraction. Magnetic fields interact with currents induced in conducting structures during plasma changes. Neutron damage alters strength and ductility over time. A module that begins with one set of properties gradually becomes another material. Engineers must design for the weakened state near the end of service, not merely the pristine state at installation. Yet increasing thickness for strength may reduce breeding or heat transfer. Adding more supports creates neutron shadows. Reducing material improves nuclear performance, but leaves less margin against failure. The optimal blanket exists at the intersection of nuclear physics, thermal engineering, chemistry, fluid mechanics, structural design, and maintenance. No discipline can optimize it alone. Maintenance may be the most practical test of all. Blanket modules face direct neutron exposure and are expected to degrade. They must eventually be removed and replaced using remote machines because human access may be unsafe. The interior of a fusion reactor is crowded, activated, and geometrically complex. Large modules must pass through limited openings without damaging nearby components. Coolant lines, tritium systems, electrical connections, and structural attachments must be disconnected and resealed by robotic equipment. A design that performs well in operation but takes months to repair may produce electricity too rarely to be economical. Replacement schedules affect the entire plant because blanket downtime is lost revenue. Component life and maintenance speed become as important as peak plasma performance. The blanket reveals why fusion cannot be reduced to the question of whether nuclei can be made to join. Once fusion succeeds, its neutrons create a second machine around the plasma, one that must harvest energy while rebuilding fuel and protecting everything beyond it. This layer must be thick enough to stop radiation, thin enough to preserve magnetic performance, hot enough for efficient electricity, cool enough to survive, open enough for maintenance, and closed enough to contain tritium. It must endure the very power it is designed to capture, The fusion fire may exist in the center, but the blanket decides whether that fire can become a power station, rather than a brief and expensive experiment. The materials inside a fusion reactor do not merely endure radiation, they're gradually rewritten by it. Every deuterium-tritium reaction releases a fast neutron carrying most of the fusion energy, and because the neutron has no electric charge, magnetic fields cannot guide it away. It leaves the plasma and strikes the surrounding wall, blanket, supports, cooling channels, and shielding. Over months and years, however, the accumulated damage can change the strength, shape, chemistry, and radioactivity of entire components. A metal chosen for toughness may become brittle. A smooth surface may swell or crack. A carefully designed alloy may fill with helium bubbles. The reactor slowly becomes a different machine from the one that was built, and practical fusion depends on predicting that transformation before it begins. When a high-energy neutron enters a solid, it may collide with an atomic nucleus and knock it out of its position in the crystal lattice. That displaced atom can strike others, producing a cascade of collisions. Within an unimaginably short interval, thousands of atoms may be shifted from their normal places. Some settle back into empty sites, but others remain as defects. Vacancies are left where atoms once sat, while displaced atoms become lodged between regular lattice positions. These defects alter the way the material carries stress and heat. Radiation damage is often described by the average number of times atoms are displaced during service. The measure simplifies a richer process, because two materials with similar displacement levels may behave differently depending on temperature, neutron energy, alloy composition, and the rate at which damage accumulates. Defects move, combine, disappear, or gather into larger structures. Temperature determines how easily they migrate. At lower temperatures, defects may remain trapped and harden the metal, making it stronger in one sense but less able to bend without cracking. At higher temperatures, vacancies can cluster into voids, causing swelling. The same component may face several temperature zones, so one region becomes brittle while another changes shape. A wall does not need to melt to fail. It may lose the ability to tolerate a sudden load, develop a crack at a joint, or deform enough to disturb coolant flow. Neutrons also change elements through nuclear reactions. A nucleus may absorb a neutron and become a radioactive isotope, or emit another particle and transform into a different element. This process is called activation. Fusion does not produce the same long-lived fission fragments created when heavy nuclei split, but that does not mean its structures remain non-radioactive. Steel, tungsten, copper, and other reactor materials can become activated after prolonged exposure. The exact products depend on the starting composition, including tiny impurities. An element present in a trace amount may create an isotope with an inconvenient half-life. Alloys must be selected not only for how they behave when new, but also for what they become after years in the neutron field. Helium and hydrogen production creates another form of hidden damage. Neutron reactions inside the lattice can generate these like gases, atom by atom. Helium does not dissolve easily in most metals, so the atoms gather into small bubbles. The bubbles grow at grain boundaries and defects, creating internal pressure. They can cause swelling, weaken bonds between grains, and make surfaces blister. In a fusion neutron spectrum, the rates of helium and hydrogen production differ from those in ordinary fission reactors. This matters because much of the available materials experience comes from fission environments. A steel that performs well around a fission core may degrade differently under the faster neutrons of fusion. Testing with the wrong spectrum can reveal part of the story while missing the damage that determines service life. Creating a realistic test environment is itself difficult. No existing facility can expose large engineering samples to exactly the same intense, continuous fusion neutron field expected in a power plant for many years. Materials can be studied in fission reactors, particle accelerators, and ion beams, but each method reproduces only selected effects. Ion irradiation can create damage quickly near a surface, yet it does not penetrate deeply and may not generate gases in realistic proportions. Fission neutrons reach deeper, but usually have a different energy distribution. Scientists must combine experiments with models, then extrapolate toward conditions that have not yet existed at full scale. The first wall faces one of the harshest combinations. It sits close to the plasma, receiving neutron radiation, heat, charged particles, and occasional bursts from unstable plasma behavior. It must preserve vacuum integrity and avoid releasing impurities that cool the fuel behind it. The blanket must maintain tritium breeding and heat transfer while its structure changes. Cooling channels must remain open and leak-free even as the surrounding alloy swells or embrittles. Thick walls may last longer mechanically, but they absorb more neutrons and leave less room for breeding material. Thin walls improve neutron economy, but carry smaller safety margins. Material choice is inseparable from geometry in the fuel cycle. Tungsten is a leading candidate for surfaces exposed to the plasma because it has an exceptionally high melting point, conducts heat well, and erodes less readily than many alternatives. Yet tungsten is not immune to neutron damage. It can become brittle as radiation defects accumulate. Neutron reactions can slowly convert some tungsten atoms into other elements, changing the material from within. Helium can gather beneath the surface and alter its texture. A surface that survives steady heating may crack when struck by a short, intense pulse. Joining tungsten to structural steel creates another challenge because the two expand differently when heated. The bond between them must survive repeated cycles while exposed to radiation. Reduced activation steels are designed to limit the production of troublesome long-lived isotopes. They replace elements used in conventional alloys with alternatives that become less persistent after neutron exposure. Yet reducing activation does not eliminate displacement damage, helium production, corrosion, or fatigue. Some alloys lose toughness within particular temperature ranges, creating a narrow operating window. Below the window they become brittle, while above it they weaken or creep under load. A blanket coolant may need to remain hot for efficient electricity generation, but the structural alloy may prefer a lower temperature. Neutron exposure steadily shifts the properties that define the safe range. More advanced materials may widen it. Oxide-strengthened steels contain tiny stable particles intended to preserve strength at higher temperatures. Silicon carbide composites offer low activation and high temperature capability. Vanadium alloys have favorable nuclear properties. Each brings unresolved difficulties. Ceramic composites can be brittle and hard to join or seal. Vanadium reacts readily with oxygen and other impurities. Advanced steels are difficult to manufacture in large complex structures with consistent quality. Laboratory samples may perform well, while welding, bends, joints, and repairs introduce weaknesses not present in ideal specimens. A power plant needs tons of material formed into modules, not only small samples tested under controlled conditions. Corrosion further complicates prediction. Coolants contact surfaces already filled with defects. Radiation can accelerate diffusion, change protective layers, and move elements within an alloy. A boundary that resists corrosion before irradiation may become vulnerable afterward. Tritium may permeate damaged structures more easily. The blanket is attacked from the neutron side and the coolant side at once. Maintenance planning therefore begins with the assumption that some components will not last for the full life of the plant. They must be replaced remotely because activated structures near the plasma may remain unsafe for direct human work. Robotic systems need clear access, reliable connectors, and modules that can be removed without dismantling the entire reactor. Yet modularity creates joints, and joints are potential weak points for coolant leaks and mechanical failure. Larger modules reduce the number of connections but become harder to move through restricted spaces. Damaged pieces must be transported into shielded areas and eventually stored or recycled. Fusion waste may be more manageable than spent fission fuel. But its volume could be large because substantial internal structures require periodic replacement. The question is not whether fusion produces radioactive material, but whether that material can be controlled, handled, and reduced through careful composition and design. The neutron is the bridge between the plasma and useful heat, yet it is also the agent that limits the machine's lifetime. Without it, deuterium-tritium fusion would not transfer most of its energy into the blanket or breed tritium so effectively. With it, every nearby material becomes temporary. The challenge is to make temporary components last long enough, fail predictably enough, and change slowly enough that a power station can remain reliable. Fusion materials must survive not by remaining untouched, but by continuing to function while their atoms are displaced, transmuted, and filled with gas. The reactor's deepest struggle is therefore not only to contain a star, but to build a surrounding world that can endure being altered by that star-one neutron at a time. A fusion experiment can release more energy from its fuel than was delivered directly into that fuel and still remain very far from producing useful electricity. This difference is easy to lose because the phrase net energy sounds complete. It suggests that the machine has crossed the final boundary and become a power source. In reality, fusion contains several energy boundaries, each wider than the last. The plasma sits at the center, but the facility around it includes heating systems, magnets, refrigeration, vacuum pumps, fuel processing, cooling loops, control equipment, and power conversion. A result measured only at the plasma may be a major scientific achievement, while the building as a whole continues to draw far more electricity than it returns. Understanding this distinction is essential, because fusion succeeds commercially only at the outermost boundary, where the complete station sends dependable surplus power to the grid. The narrowest measure compares fusion energy with the energy coupled into the plasma. In magnetic confinement, external systems heat the fuel with neutral beams, radio frequency waves, or electrical current. In inertial confinement, lasers or particle beams compress a tiny target. Scientists often define a gain factor by dividing the energy released through fusion by the energy that actually reaches the fuel. A value below 1 means the plasma or target receives more energy than fusion gives back. A value above 1 means the nuclear reaction releases more energy than the directly coupled input. This is an important threshold because it shows that the fuel itself has begun to amplify the delivered energy. Yet the input reaching the plasma is only part of what the facility consumes. Heating systems lose energy before it arrives at the fuel. A neutral beam begins with electricity used to create ions, accelerate them, convert them into neutral atoms, and guide them through the reactor. Not every particle reaches the plasma, and not all of its energy remains in the useful region. Radio frequency systems first convert electrical power into precisely tuned electromagnetic waves. The generators, transmission lines, and launchers all have losses. Laser facilities face an even sharper difference. Electricity from the grid powers laser equipment, but only a fraction becomes laser light, and only part of that light reaches and compresses the target in the desired way. A target can therefore produce more fusion energy than the light striking it, while the laser system consumes many times that amount from the electrical supply. Scientific gain measures the physics of the fuel. It does not measure the efficiency of the path leading to it. The magnetic system creates another large demand. Conventional copper coils lose energy as heat, while superconducting magnets can carry enormous currents with almost no electrical resistance. Superconductivity, however, requires extreme cooling. Cryogenic plants must remove heat that enters through supports, wiring, radiation, and neutron leakage. Extracting heat at temperatures near absolute zero requires far more work than removing the same amount at ordinary temperature. The magnets also need protection, monitoring, and power conditioning. During changes in operation, large amounts of magnetic energy may be stored, moved, or safely discharged. A stronger magnetic field can improve plasma performance and reduce reactor size, yet the supporting structure must resist immense forces. Vacuum systems operate continuously because the plasma chamber must remain almost empty except for carefully controlled fuel. Pumps remove stray gases, helium ash, unburned isotopes, and impurities released from surfaces. Fuel processing equipment then separates deuterium and tritium, cleans them, measures the inventory, and returns them to the reactor. Tritium bred in the blanket must be extracted from solids or liquids, purified, and moved through secure containment. Coolant pumps force water, gas, liquid metal, or molten salt through channels under difficult conditions. Remote handling equipment, diagnostics, computers, safety systems, and ventilation all require electricity. The next boundary is engineering break-even, where the energy produced by the reactor is enough to cover the energy consumed by the entire fusion facility. This threshold is much harder than plasma gain above 1. The fusion output must first be captured. In a deuterium-tritium reactor, most energy leaves in neutrons and becomes heat in the blanket. That heat must move into a coolant and then through a power conversion cycle. Every transfer loses part of the original energy. A steam turbine cannot convert all heat into electricity because thermodynamics places a fundamental limit on efficiency. Real turbines, pumps, generators, and heat exchangers add further losses. If a reactor produces several units of thermal energy, only part becomes electrical output. Some of that electricity must immediately return to the plant to operate its supporting systems. The remainder is the true net supply. This creates a recirculating power problem. A fusion plant may generate a large amount of electricity while consuming a large fraction of it internally. The station could technically produce net power, yet deliver too little to justify its cost. Commercial operation needs a comfortable margin, not a narrow victory. A plant that sends only a small surplus to the grid remains vulnerable to temporary increases in heating demand, reduced turbine efficiency, component degradation, and maintenance outages. It must produce enough gross electricity to support itself and still sell substantial power over its operating life. The gain required at the plasma therefore depends on the efficiency of everything around it. If external heating is inefficient and the thermal cycle converts only part of fusion heat into electricity, the plasma gain must rise far above unity. A modest gain can prove that confinement and fuel performance are improving without being sufficient for a station. Designers often seek burning plasma conditions because self-heating reduces the need for external power. In deuterium-tritium fusion, helium nuclei born in the reaction remain magnetically confined and transfer energy back to the fuel. As this internal heating grows, outside heaters can provide a smaller share. Ignition represents the limiting case in which fusion products maintain the plasma temperature without continuous external heating. Even ignition does not eliminate plant loads. Magnets, pumps, fuel systems, controls, and heat conversion still operate. Duration matters as much as instantaneous gain. A brief pulse may reach a remarkable energy ratio, but contribute little average power over a day. A commercial station must repeat pulses rapidly, or sustain the plasma for long periods. Between pulses, magnets may recharge. Chambers may be cleaned, targets may be replaced, or structures may cool. These intervals reduce capacity factor, the fraction of time the plant produces useful power. Electricity markets value reliable output, so a reactor that performs brilliantly for seconds and rests for hours is not a practical generator. The energy spent preparing each pulse must also be included. A complete accounting begins before fusion and ends only after the plant is ready to operate again. In inertial fusion, repetition exposes a particularly severe gap between experimental success and power production. A scientific facility may fire a small number of high-energy shots, with each target manufactured and positioned carefully. A power station would need to produce, deliver, and ignite targets repeatedly, perhaps several times each second, while protecting the chamber and recovering heat. The driver must operate efficiently and survive an enormous number of cycles. A target gain impressive in isolation may still be too low once laser efficiency, target production, chamber clearing, and turbine losses are counted. Magnetic reactors face a different version of the same issue. They may sustain plasma longer, but they require continuous current drive, cryogenics, exhaust, fueling, and cooling. Neutron damage forces component replacement. Every shutdown lowers lifetime electrical output while costs continue. The economic value of a reactor depends not on its best pulse, but on the total electricity sold across decades. Reliability changes the energy story because frequent repairs consume power, labor, spare parts, and time. A plant that reaches high gain but rarely operates can lose to a simpler technology with lower peak performance and higher availability. The language of milestones therefore needs careful boundaries: scientific break-even, target gain, plasma gain, engineering break-even, and commercial net power describe different achievements. Crossing an inner boundary proves that a particular physical obstacle can be overcome. The next boundary then reveals losses that were previously hidden by the narrower measurement. Fusion advances through these nested circles, from individual reactions to self-heating plasma, from plasma to reactor, and from reactor to power station. The final requirement is not merely that fusion energy exceed some selected input. It is that the entire machine operate as an energy system rather than an energy experiment. The station must generate heat, convert it efficiently, power its own organs, survive interruptions, and deliver enough electricity to repay the energy and resources invested in building it. Net energy becomes electricity only after every hidden load has been counted. Until then, a successful plasma can glow at the center of a facility that remains, in the broadest sense, an electrical consumer. The final barrier to fusion is not a single piece of physics. It is the requirement that every piece of the machine succeed together, not once, but repeatedly, predictably, and at a cost the wider energy system can accept. A reactor may confine a hot plasma, breed some tritium, withstand neutron exposure for a period, and produce more fusion energy than reaches the fuel, yet still falls short of becoming a power station. Commercial fusion demands an entire operating chain. Fuel must be available before startup. Magnets must create the correct field. Heating systems must bring the plasma into its working range. Control systems must prevent instability. Blankets must capture neutrons, remove heat, and breed enough tritium. Materials must survive long enough to justify replacement. Maintenance equipment must restore damaged components without months of delay. Turbines and generators must convert heat into electricity efficiently. The plant must then deliver power often enough to repay the extraordinary cost of construction. Fusion becomes practical only when the weakest link in this chain becomes strong enough. Reliability changes the character of every scientific achievement. An experiment can be tuned for a record pulse, operated by a large research team, and paused for careful inspection afterward. A power station must perform under routine conditions. It must start when scheduled, remain within safe limits, recover from small disturbances, and continue operating through the ordinary imperfections of machinery. Pumps wear, valves stick, sensors drift, seals leak, surfaces erode, electrical systems fail. In conventional plants, these events are familiar maintenance problems. In fusion, many components sit behind thick shielding or inside activated structures where direct access is impossible. A small failure in the wrong location can stop the entire reactor while remote systems diagnose and repair it. The design must therefore consider not only whether each component works, but how it fails and how quickly it can be replaced. Availability, the fraction of time a plant is able to generate power, becomes as important as plasma gain. A reactor that produces immense power during operation but remains offline for long repairs may generate little electricity over a year. High neutron flux ensures that some internal components will need periodic replacement. The first wall, diverter, and blanket are expected to face the greatest damage. Their service lives may be measured in operating years or less, depending on materials and conditions. Replacing them means disconnecting coolant lines, tritium systems, supports, diagnostics, and electrical connections in a radioactive environment. Robotic tools must identify worn modules, release fasteners, cut or seal pipes, move heavy components through narrow ports, and install replacements with precise alignment. Every step must work despite dust. Radiation, limited visibility, and changing material properties. A maintenance procedure that appears feasible in a drawing may become slow and uncertain inside a real machine. Plant layout must therefore be designed around removal paths and repair access from the beginning. This competes with the desire to place magnets close to the plasma, maximize breeding material, reduce reactor size, and minimize openings through the blanket. The most compact machine is not necessarily the easiest to maintain. Component lifetime also shapes the cost of electricity. Advanced alloys, superconducting magnets, precision coils, tritium systems, shielding, and remote handling facilities are expensive. If critical parts must be replaced frequently, the plant pays repeatedly for specialized materials and long shutdowns. If designers increase thickness and redundancy to extend life, the reactor becomes larger and more costly to build. Fusion economics, therefore, cannot be separated from materials science. A small improvement in neutron resistance may add years of operation and reduce replacement frequency, while a modest increase in repair time may erase the benefit of higher plasma performance. The cheapest kilowatt-hour may come from a reactor with slightly lower peak output but simpler components and faster maintenance. This is why the best physics design is not automatically the best power plant design. Construction cost forms another barrier. Large magnetic fusion devices require immense precision over structures measured in many meters. Superconducting coils must be manufactured, supported, cooled, and protected from forces that try to pull them apart. Vacuum vessels and blanket modules must fit within tight tolerances. Heavy shielding surrounds the core. Tritium processing buildings, turbine halls, cryogenic plants, power supplies, and cooling systems expand the site far beyond the plasma chamber. First-of-a-kind projects carry additional cost because manufacturing methods, regulations, and supply chains are still developing. Delays increase financing expenses, and unique components are difficult to replace. A commercial industry would need standardized designs, repeatable construction, trained workers, qualified materials, and suppliers able to produce specialized parts at scale. Fusion must move from scientific craftsmanship toward industrial routine. That transition has defeated other complex technologies even after their basic function was demonstrated. Regulation and safety shape the path as well. Fusion lacks the possibility of a runaway chain reaction like that associated with fission, and the amount of fuel in the plasma at any moment is small. If confinement fails, the plasma cools and fusion stops. These are important advantages, yet a fusion plant still contains tritium, activated materials, strong magnetic fields, cryogenic systems, stored electrical energy, high-pressure coolants, and large thermal loads. Regulators must define acceptable inventories, containment systems, waste categories, emergency procedures, and worker exposure limits. Rules that are too weak can undermine public trust, while rules copied directly from fission may impose requirements poorly matched to fusion's different risks. A clear and stable framework is necessary before companies can finance and build fleets of reactors. Public acceptance will depend less on slogans about limitless clean energy than on transparent evidence that fuel, waste, accidents, and decommissioning are managed responsibly. Fusion also enters an energy landscape that does not stand still. While reactors are being developed, solar power, wind power, batteries, transmission systems, geothermal technologies, fission reactors, and demand management continue to improve. Fusion does not compete with the world as it existed when research began. It must compete with whatever technologies are available when commercial plants arrive. A reactor that produces low-carbon electricity may still be unattractive if it costs far more than alternatives or takes too long to build. Its strongest value may not be the cheapest energy at every moment. It may provide steady output when weather-dependent sources are low, supply high-temperature heat for industry, produce hydrogen or synthetic fuels, or support regions with limited land and few energy resources. The economic case depends on the role fusion plays within a wider grid, not only on the performance of the reactor in isolation. Different fusion concepts try to alter this balance. Some pursue smaller machines using stronger magnetic fields. Some seek simpler linear geometries. Some compress plasma in rapid pulses. Some aim to convert the energy of charged particles directly into electricity rather than first making steam. Some hope to use fuels that release fewer neutrons. Each approach removes certain burdens and introduces others. A compact machine may face harsher heat loads. A pulse device may suffer fatigue. Direct conversion may require fuel cycles with more difficult physics. Advanced fuels may reduce activation while demanding much higher temperature. Novel designs can be valuable precisely because the conventional path is so demanding. But novelty does not excuse the complete power plant test. Every concept must eventually answer the same questions about fuel supply, component life, net electricity, maintenance, safety, and cost. No single record can replace that accounting. The long history of fusion is often described through disappointment, yet the repeated delay carries another meaning. The field has moved from asking whether fusion reactions can be created to asking whether burning plasmas can be controlled, whether tritium can be bred, whether materials can survive, and whether complete plants can operate economically. Each new question appears because an earlier one becomes more clearly answered. The horizon recedes because the destination gains detail. What once looked like one barrier is now understood as a landscape of connected limits. This knowledge does not guarantee success. but it transforms hope into engineering choices that can be tested. Fusion remains difficult because it requires mastery across nuclear physics, plasma behavior, superconducting technology, robotics, materials, chemistry, thermodynamics, regulation, and industrial economics. It asks a civilization to build a machine in which star-like conditions exist beside cryogenic magnets. Radioactive hydrogen circulates through sealed systems, damaged walls are replaced by robots, and every lost unit of energy is counted. The reaction at the center is brief and simple. Two light nuclei combine, and energy emerges. The power station around that reaction is the true invention. Only when the entire system becomes durable, self-fueling, repairable, efficient, and affordable does fusion cross its final boundary. Until then, the plasma can prove that the fire is possible while the unfinished machine around it explains why the fire is still so difficult to keep.